Hi, welcome back to another episode of Algebra and Words, the video series on YouTube. In this video, we're going to pick up on where we left off on the last video, which is an overview of two systems of linear equations and systems of two linear equations. Now, where we left off last time was an overview, but in this episode, before we get to the methods of solving, we're going to look at what are basically called the three types of systems of linear equations. And before we get to that, if you want to read about that in my book, Algebra and Words, you could read this in written form on page 67 and 68 in the book, Algebra and Words, which is on Amazon, and you'll see the link for that in the description box below. So let's take a look. When you have a system of two linear equations, they can basically be categorized into three types of systems. They could be intersecting, they could be parallel, or the lines could actually be overlapping. Okay, now let's start with the intersecting type. And okay, what you want to get out of this video is not only will you ultimately want to be able to solve systems of two linear equations, okay, and analyzing what the type of outcomes and solutions mean, but sometimes a question on a test might ask you to define the type of system. So that's what I'm going to help you do in this video. Alright, now, one type is the two lines just simply intersect. Okay? I have two graphs to show that. This one and this one. Let's look at this one first. The lines just intersect. And when they intersect, they have one point in common. And the point in common is the solution, because the solution to the system of two linear equations is the point where they cross, and it's 1 point. Okay? And in that case, we call that system consistent, and we also say that their equations are independent. Now, again, in that case, there will be only one solution, because for lines to intersect, they can only cross in one place and have only 1 point in common. At this point, I like to do something that most books don't really do in their little description box, and that is there's sort of a subcategory of intersecting lines. Okay, they could just intersect randomly, but what about in a graph like this? If you notice, they intersect at a perfect 90-degree angle. Okay, and we would also call that perpendicular lines. So that's why I have a little asterisk here with a note that shows intersecting lines can be perpendicular, okay, and how do you know that? You know that because if you have both equations in slope-intercept form, and you notice that the slopes of each other are opposite reciprocals of each other, that's a sign that the slopes are perpendicular, that they intersect at a 90-degree angle, the lines are perpendicular to each other. Also, it means that they're intersecting and they have one solution. So this is just a subcategory of intersecting. Okay, that's pretty standard, but then in the next two categories are the ones that sometimes students are not as familiar with. So let's focus on them next. Okay, the next possibility is you have two lines, and if you look at the graph, they're parallel. Okay, one thing that we know about parallel lines that you probably know from before or previous videos is, again, if you have both equations in slope-intercept form and you look just at their slopes and the slopes are identical, then that tells you that the lines are expected to be parallel. Okay? So when you have a system of equations that are in which the lines are parallel, we call that type of system inconsistent. Okay? Why? Well, let's talk about the solutions. There's no solution. Okay? And how do we know that? Well, there can't be solutions because they don't intersect. So that's why there's no solution. But also, let's look at one other way that we can tell whether the lines are parallel and the system is inconsistent, supposing that we didn't have the graph to look at. Okay? And here's how you would do it. Suppose you were given two equations and you were trying to find the solution. In other words, using one of the three methods to solve the system of two linear equations. Okay, so you do one of the methods, suppose it's the substitution method, and you get down to the later steps, and what you ultimately find is you would ultimately run into something that doesn't make sense. For example, this is just an example. Suppose you simplify it down and you got something like 5 equals negative 7. Well, obviously they don't equal, that's impossible. This is the sign where you say no solution. Then when you say no solution, if you're asked why or what type of system is it, you say it's an inconsistent system because the lines are parallel. And that's pretty much all you need to know about that. Again, if you didn't have the graph and you wanted to check in another way, put the equations both in slope-intercept form, compare the slopes, and if they're the same, that's another clue to tell you that what you thought is true. They're parallel lines, inconsistent system, there's no solution, and that's pretty much it. Now let's look at a third possibility. Another possibility is you're given two equations, okay? Maybe you graph them, maybe they're graphed for you already. And in this case, what you're going to see on the graph looks like one line, okay? Each textbook calls this a little something different. I call these overlapping lines, okay? But they do look like one line. Usually in a textbook where they demonstrate these with graphs, they'll show one line as red and one line as blue, but then when they get to this graph, usually the line is purple, and that's to insinuate that it's a red line and a blue line overlapping, mixing the color, making purple. So let's analyze this a little bit. So we have overlapping lines, okay? In that case, we would call the system consistent, okay, as opposed to inconsistent for when they never touch. We would call the equations dependent. And also, what about the solutions? In a case of overlapping or a dependent system, they have infinite number of solutions. So if you were doing a problem like this, and however you got to the end of the problem, you knew that they were overlapping lines, your answer would be infinite solutions. Okay, but let's look at that a little step further. And how might you tell that, supposing you didn't have the graph? Okay, once again, suppose you're given two equations and you're using one of the methods. Let's say this time randomly the addition-elimination method. And you're doing the method and you're doing the math, but ultimately when you start simplifying down and get near the end of the problem, again, something that it does make sense, but it seems to be a little off. And it could look like where a number equals a number. Okay, now in this case they do equal. In this case they didn't equal, but in this case they might equal. It could be 3 equals 3. Or it could be another situation where if you simplify all the way down as much as possible, then you could see 0 equals 0. Both of these signs are signs that there are infinite solutions, because you could put the same multiple points. They do have to be ordered pairs. In other words, they do have to be points that fall on the line. They can't just be any random points. But there could be multiple points on this line that you substitute the value of x and y into both equations, and the left side and the right side just completely cancel out to 0, leaving 0 equals 0. And that's one sign by doing the math that you have a dependent system of overlapping lines. There's actually one other way you can tell as well, okay? And the other way to tell is it's sort of a visual check of the equations. And here's what I mean. The first thing that you would have to make sure of is both equations would have to be in the same format. So for example, both would either have to be in slope-intercept form, or both would have to be in standard form. Okay, usually if you're doing a system of two linear equations, they tend to come in standard form, and when you're doing the math, I tell you to put them in standard form. So assuming that the equations are in the same form, let's say standard, okay, in the case of dependent system, if you reduced down each equation as much as possible, for example, either by eliminating any fractions if there are any, or if there's any common factors, let's say that all the terms have a common factor of 3, and you divide that out, then you would ultimately notice that the equations are the same. All right? They may not start out as the same because one of them may have a multiple multiplied through them. Okay, but if you reduce both of them down as much as possible in, say, standard form, you'd notice that the equations are literally identical, and then that, again, would be another clue to tell you you're dealing with a dependent system, which when graphed would give you over